So far, we have not considered how we handle distributed loads in plastic analysis. All that we have indicated is that the plastic hinge can form somewhere underneath the distributed load. The exact location of this plastic hinge depends upon the relative magnitude of the central bending moment and the end bending moments in the structure. There is a method, however, to be able to identify where the plastic hinge is located and then how you can do a subsequent plastic collapse analysis. In order to do this, we begin by assuming that at first the plastic hinge occurs at the midspan. After this, you perform your usual plastic analysis, and then, using a statical procedure, you determine the end moments and finally determine the maximum bending moment along the beam and its corresponding location. At that point then, static checks can be performed and any necessary reanalyses can be conducted. For the statical procedure, we use the following formula to work out the location and magnitude of the maximum bending moment. Taking any segment from your structure, AB, with the distributed load along it of magnitude W, we can then work out what the reactions are and consequently where the location of the maximum bending moment is, and finally what the actual maximum bending moment is. For the reactions, we say that RA is equal to W times L over 2 plus MA minus MB over L. The location of the maximum bending moment is given by X max, and that's equal to RA over W. And finally, M max is given by MA plus RA times by X max minus W times X max squared divided by 2. The best way to understand how this is to be used is through an example. In this example, we have a rectangular portal frame with height 4 and width 8, a distributed load of 5 lambda kilonewtons per meter, and a concentrated horizontal load of 20 lambda. M plastic is assumed to be 40 kilonewtons in meters, and alpha is 3, C is 5, and the number of basic mechanisms, N, is 2. For mechanism 1, as we said before, we assume the plastic hinge develops at the midspan. To make the analysis slightly more accurate, we're taking the distributed load and applying it halfway along each half span. Again, we have angles minus theta, and 2 theta at plastic hinge locations. And at the center, we have displacements dCV. It can also be shown that underneath the loads, the displacements at this point are given by 2 times theta. The displacement then dCV is equal to 4 theta. Performing virtual work, 20 lambda times by 2 theta, which is the first concentrated load, plus 20 lambda times by 2 theta, which is the second concentrated load, is equal to mb minus theta plus mc 2 theta plus md minus theta. For the purpose of performing static checks, we will call this equation 1. At collapse, 80 times lambda 1 theta is equal to 4 b theta. So lambda 1 is equal to 2 mp over 40, which with mp being equal to 40 is equal to 2. So lambda 1 is equal to 2, and the collapse load factor is less than or equal to 2 at this stage. For mechanism 2, we have a sway mechanism. With deformation angles minus theta, theta, minus theta, and theta, and horizontal displacement delta d h. Delta CV is 0, and delta d h is given by 4 times theta. By virtual work, then 20 times lambda times 4 theta is equal to ma minus theta plus mb times by theta plus md times by minus theta plus me times by theta. For our static checks, we'll call this equation 2. At collapse, 80 times by lambda 2 times by theta is equal to 4 mp theta. So lambda 2 is also equal to 2, and lambda collapse is still less than or equal to 2. Our combined mechanism, which can be determined by summing up the two basic mechanisms, has a plastic hinge at A, C, D and E, with deformation angles determined from summing up the contributions from mechanisms 1 and 2, minus theta, 2 theta, minus theta and minus theta, and theta. The deformations under the load are DC, V, and horizontal deformation D, D, H. DC, V is equal to 4 theta, and DD, H is also equal to 4 theta. performing virtual work gives us 2 times 20 lambda times by 4 theta, which is the vertical contribution, plus the horizontal contribution of 20 lambda times by 4 theta. And that's equal to MA times minus theta plus MC times by 2 theta plus MD times by minus 2 theta plus ME times by theta. At collapse, we have 160 lambda times by theta equal to 6 MP theta. So lambda 3 is equal to 1.5 and the collapse load factor is less than or equal to 1.5. If we now perform static checks, we realize that the bending moment at B with this lowest collapse mechanism with lambda c being equal to 1.5 is unknown, but elsewhere the bending moment is known. And this comes from the values obtained from collapse mechanism 3, the combined collapse mechanism. MA is equal to minus MP, MB is unknown, MC is equal to MP, MD is equal to minus MP, and ME is equal to MP. So MB needs to be checked, and we can do this using equation 1 because this features MB, and we can substitute in the values for the remaining components from the third mechanism. So we have 40 times by lambda times by 2 theta is equal to MB times by minus theta plus MC times by 2 theta plus MD equal to minus theta. We know that this is equal to MP. We also know that this is equal to minus MP in the diagram above. We also know that this is equal to 1.5. Upon substituting these values into this equation, we find that we have 120 equal to 120 minus MB. So that implies that MB in this case is equal to 0. And so MB is less than MP, and we don't have any yield violations. This could potentially be the correct collapse mechanism. However, as we've said, we've assumed that the plastic hinge location is in the center. As a result of this, we need to determine the exact location of the plastic hinge, and we need to then do a subsequent check on whether or not this is correct. So now reconstructing our first figure by substituting in the correct values, we find we've got a distributed load of 5 lambda. MB in this case is set equal to 0 because we have just determined that. MD is equal to minus MP, which is equal to minus 40. MC is equal to MP, which is equal to 40. and lambda equal to lambda c is equal to 1.5. With this information to hand, we can then substitute these values into the formulas given. So RB is equal to W times L over 2 plus MD minus MB divided by L, and that's equal to 5 lambda times by 8 over 2 plus minus 40 minus 0 divided by 8, and that's equal to 5 times by 1.5 times by 8 over 2 minus 40 over 8, which is equal to 25 kilonewtons. X max then is equal to RB over W, which is equal to 25 over 5 lambda, which is equal to 25 over 5 times 1.5, which is then equal to 33.33 meters. M max is then equal to MB plus RB times X max minus W times X max squared over 2, and that gives 41.67 kilonewton meters, which is greater than MP, which is equal to 40 kilonewtons meters. So, as a result of this, we have a yield violation. So as a result, we need to scale down the moments, and subsequently we also need to scale down lambda c. Currently, lambda c is equal to 1.5, MA is equal to minus 40, MB is equal to 0, MC is equal to 41.67, MD is equal to minus 40, and ME is equal to 40. With this information to hand, we scale down MP by M max. We end up with a factor 0.96, and we can then derive a new plastic collapse load factor, lambda c starred, which is equal to lambda c times by 0.96, which is equal to 1.44. The new moments then are MA equal to minus 38.4, MB equal to 0, MC equal to 40, MD equal to minus 38.4, and ME equal to 38.4. We can then say that 1.44, the plastic collapse load factor, is bounded by 1.44 and 1.5.